Good afternoon, morning, evening, wherever you are, whatever you are. Glad you're here. Welcome to another Takeo Tuesday. And I'm sure it's the last one of the year. I shouldn't say that. I guess there could be one next week. I know Rich and I will not be putting it on. So my name is Brett Zerba, as most of you know, and Rich Medairos will be the main presenter. He'll do a nice introduction of himself very shortly. Today's presentation is on kind of a lost art. Some fundamentals of hydronic piping system, pressure loss, drop, manual calculations. And Rich does a really good job of breaking it down, the old point-to-point method. I remember learning that in 1981 when I first got out of school from the University of New Hampshire. If a couple of you could raise your hand so I know that you can see my screen and hear me talking. Oh boy, couple hands up, please, couple. Rich, can you hear me?
I can, yes, loud
All
and
right.
clear.
Okay, Andy. Thank you, Andy. Thank you. I know it's kind of silly. We've been doing this for 2 years now, maybe longer. I don't even know. Everything's that 2 week shutdown's getting on my nerves. Thanks, Gordon. Appreciate that. Sounds fine. Well, good morning to everybody. Good afternoon. I see someone else from Portland, Oregon. Brian, thank you for joining us. Um, uh, Takeo Thermal Appliance Company. I'm actually at the factory today. I'm sitting in. Some of you, I see some names I recognize out here, sitting in the IDC center that Rich and I enjoy meeting folks like yourselves when we get to do in-person training. And we're putting quite a program together for next year. So please rattle your reps' cages and tell them you want to come to the factory, get a nice tour of our two facilities that are the headquarters in Cranston, Rhode Island, and then our welded products facility, which is always a great tour. They actually bend metal and weld metal down there. It's pretty amazing. Both factories are great tours, but nonetheless, those programs will start up in the spring sometime. So, anyways, uh, most of you know the history of Takeo. It was on the screen for a while. We're a 101-year-old company. We will be at ASHRAE. We will be at ASHRAE. So if anyone's going to be going to ASHRAE, we will be at ASHRAE, which is it was canceled last year. It's supposed to be in Chicago. This year it's in Las Vegas. But we will be front and center, and there will be a nice big party, the Monday night party. Make sure you get your wristband. Come by the booth or talk to your Takeo rep, and they can make sure you're registered and you can pop in and socialize with us and whatnot. It's a big open space, probably the biggest space we've ever had. So there should be enough room for social distance if you'd like, and be safe. So anyways, hopefully we get to see some of you out there. I know Johnny will be out there and Cheryl will be out there. So Johnny's two boys are planning to attend as well. So, and Rich and I will be at the booth. Although they don't put us in the booth together, so it's kind of he has to work one shift and I work the other shift. So we don't get to do our vaudeville act together when we're out there. But most of you know how experienced Rich is in this field. So please, I can't emphasize enough. Ask your questions. I'll be monitoring the questions. Type them in, and we'll get them out there. Some of this stuff is relatively basic, but it's important to know. We are firm believers in that you need to know the basics, the fundamentals, and so then you can really take things off. And I know from personal experience, being at some other companies prior to my 25 plus years here at Takeo, sometimes when they bring you in, they don't necessarily you don't get to taught the basic stuff that are building blocks to everything we do on a daily basis, and sometimes at least that's my feeling on that. So that's why this class is it's important, and it could re-emphasize some things that some if not most of you already know, but nonetheless very important stuff. Some if you're going to specify pumps and size pumps, you get the flow rate, but then you need that head loss, right? Well, this is how you can do it the old-fashioned way that Rich and I used to when we first started in this industry. But thank God for computers. Thank God for computers, and Rich will go over that as well. So I think that's enough yapping for me. 24 hours after, you'll get the access to the recording. It is being recorded. By the way, all of these Taco Tuesdays are available on our website. You might have to do a little searching or on the YouTube Taco YouTube channel, but any one of the ones that we've done are available. So obviously you get the recording or a link to it sent to you, as well as your certificate if you need that. But nonetheless, keep that in mind. But other than that, I think that's enough introductions. There are no handouts today, so don't be looking for that. Don't be looking for that. But please type questions, and happy holidays, Merry Christmas, Happy New Year, and any other celebrations that are going on out there. Enjoy it. It's kind of, we had a meeting the other day, and you get to catch your breath a little bit come Friday to maybe the 3rd or 2nd or 3rd of January. So if that's where you are, catch your breath and then get ready to start 2022 on a gangbuster. That's what we want to do. So I'm done yapping, Rich. Take it away, my friend.
Well, thanks, Brett. A great introduction. Just a very short introduction for myself. My name is Rich Medairos, one of the senior systems engineers here at TACO. I am a mechanical engineer, registered in a couple of states as a professional engineer, and I've been in the business a few years. I do specialize in the engineering design of HVAC systems. And today we're going to talk about the fundamentals of pressure drop or pressure loss calculations. We're going to do the manual method, which is the basis by which most software pressure drop calculations are modeled after. And today the methodology that we're going to use is the point-to-point method. So one of the things we're going to cover, first of all, I got to get the thing to advance here. We're going to talk a little bit about design criteria, and I'll tell you what that means in a minute. Water velocity is an important piece of the pressure drop calculation, and water velocity pressure. We're going to talk about pipe pressure loss, fitting pressure loss, valve pressure loss. And we're all going to also define what a valve CV is, or valve pressure drop coefficient. And questions. And as Brett said a moment ago, please ask your questions during the presentation. Brett will ask me to pause periodically so we can answer your questions. And then if we do have some time at the end, we'll take as many questions as possible. But you do not have to wait until the end. So hopefully you'll participate. Okay, so what do we mean by design criteria? Whenever you talk about doing a pressure drop calculation or designing a piping system, you have to establish some type of design criteria at the beginning of your process. And so I'm just going to put in a few components of that design criteria. We're going to set the maximum velocity for our piping system at 8 feet per second. 8 feet per second. We're going to have a maximum pressure drop of 4 feet per 100 feet. That'll be our upper limit for our pressure drop calculations. In our case, the fluid will be clear water, and that's important because when you do pressure drop calculations, if you have, for example, a propylene glycol mixture or an ethylene glycol mixture, it will change the pressure drop characteristics depending on the fluid that you're using. Specific gravity is 1.0, and again, that relates to water. Maximum fluid temperature for our example today will be 180 degrees Fahrenheit. So now that we have that design criteria, let's talk a little bit about the properties of some pipe as it relates to velocity. Now, one of the things I always like to try to point out is that when we talk about pipe, we're talking about, relative to pressure drop calculations, we're talking about the inside diameter right here. And today we're going to start with this little example. Given a 6-inch Schedule 40 steel pipe flowing 500 gallons per minute, we're going to want to figure out what the velocity is going to be in feet per second. And the important thing to keep in mind is that when it comes to piping systems, for a given pipe size, in this case it's a nominal 6-inch, it has an outside diameter of 6.625 inches. And because it's Schedule 40 pipe, as opposed to Schedule 80, which is a stronger pipe, The inside diameter, let me do it this way first. The outside diameter remains fixed for different strength pipe, but the inside diameter decreases as the strength of the pipe increases, or the inside diameter increases as the strength of the pipe decreases. So for example, if you're using Schedule 10, which is fairly common for sprinkler systems, we're not going to cover sprinkler systems today, but just as an example, Schedule 10 pipe will have a larger inside diameter. In other words, the wall thickness will be smaller for Schedule 10 than it will be for Schedule 40 in our case. And then if you go up to, for example, Schedule 80, the wall thickness will get even greater. The outside diameter remains fixed, but the inside diameter changes. So you need to be aware of that concept, because if you are designing a system and you're doing the pressure drop calculations, and you might assume that you have Schedule 40 pipe, and for some reason they may actually be using Schedule 80 pipe, maybe it's an existing system, and you have to make sure of what pipe type you're using so that you can calculate the appropriate velocity. Now, there are tables out there, but that's the good thing today. You can just Google if you want pipe tables for any type of Schedule 10, Schedule 40, Schedule 80, those are probably the most common, but there are other schedule pipe sizes out there. And they'll give you the inside pipe diameter or the velocity based on a certain flow. Okay, so the next thing we want to talk about is, I'll keep going here for a second. Let me erase some of this stuff. Any questions, Brett, while I transition?
Good shape.
I'm sorry, I couldn't hear you just then.
I said no
Okay.
questions.
All right. So we're going to calculate the pipe internal area in square feet in order to figure out what the velocity is. So the interior area is simple. There's a very simple equation. Most of you are familiar with it. It's called the pi d squared divided by 4 divided by 144 square inches per square foot. So we want the area in square feet, which is why we use this conversion factor over here. And that comes out to an internal pipe area of 0.2006 square feet. So the velocity is equal to the flow in gallons per minute divided by the cross-sectional area in square feet times this constant here, and that 449.4. I'll tell you where that comes from. So if you do these numbers, you put it in your calculator, you'll come out with 5.55 feet per second. I think you can hear my dog in the background. Hold on, Brett.
Yeah. I just remember when I was more involved with designing systems, a lot of times some people will ask, why do you need stronger pipe? And it's usually in HVAC, it has to do with pressure, maybe in a high rise or something like that, or whatever. So that may be one reason. So that could be.
Yeah, in fact, sometimes it's not a pressure issue. It could be simply, you might have a riser, for example. I did a project several years ago where the pipe was, excuse me, the bottom of the building was a vertical riser. I think it was large pipe. I think it was like 16 inches in diameter. And the riser went from the lowest level in the building all the way up to the top floor. And I think the first 5 floors of the building, we actually used Schedule 80 pipe in order to support the weight of the pipe that was above it. So there's a variety of reasons why you might consider using a stronger pipe. So in this case, we did the calculation. It comes out to 5.55 feet per second. And that constant that was in that equation, that's equal to 449.4 is equal to 7.49 gallons per cubic foot times 60 seconds per minute. That equals the weirdest units, but it's 449.4 gallon seconds per cubic feet minute. And that is the conversion that you need to get into feet per second. Okay, so let's look at this table over here that I got from the internet. Again, you can look up, there are all kinds of tables available for the internet. We have a 6-inch pipe. We just said we had a 6-inch pipe, and we're pumping, moving 500 gallons per minute. And under this column of velocity right here for Schedule 40 pipe, you'll notice that the value is 5.55 feet per second. So that's exactly the same value that we just calculated a moment ago. You know, whenever I use a pipe table, I always do a quick hand calculation to make sure that the table is appropriate. In other words, if I did the hand calculation and the velocity came out different than what's in this table here, then I'd know I'd have either the wrong pipe size that I'm basing my calculation on, or the pipe table is for a different pipe configuration. But this is Schedule 40 steel pipe. Okay, continue along here. Let's go to the next little quick calculation here. So again, given a 6-inch Schedule 40 steel pipe at a flow of 500 gallons per minute, we want to calculate the velocity pressure, or the head, in feet. And in this case, the velocity pressure is equal to the velocity in feet per second squared divided by 2 times the gravitational constant. And that's, I'll show you where we get that value in a second. So we just moments ago calculated the velocity of 5.55 feet. You square that and divide that by 2 times the gravitational constant. The gravitational constant is 32.2 feet per second squared, and therefore the velocity pressure comes out to 0.479 feet. And again, that's the G value in this equation is the gravitational constant of 32.2 feet per second squared. So let's go back to our table once again. Take a quick look at our table. Again, 6-inch pipe, exactly the same values that we looked at a moment ago. There's 500 feet per second. We already pointed out what the velocity is, feet per second. There's the velocity head in feet. And if you'll notice, that velocity head is 0.479. That's exactly what we just calculated. So that's where that value comes from. Any questions, Brett?
No, question free right now.
A question-free afternoon. Well, there you go. Okay, so now let's look at what we call the equivalent length method for fittings. So when we look at a straight piece of pipe, let's talk about a straight piece of pipe first. Let's say I had a piece of pipe, straight piece of pipe, nice straight piece of pipe. And I could look up in a table, and I'm going to do that in a minute. But the data was on the previous table. Let's assume that this piece of pipe was exactly 100 feet long. And again, in our case, that's 100 feet, 100 feet. Yep. So let's say that we had this straight run of pipe. And in our example, let's assume it was 6-inch diameter. And we were pumping and or moving 500 gallons per minute. Let's go back to that previous table for a moment. Let's see if I can do this without messing this up. So there's that 6-inch pipe, and here's the friction loss in feet. And if you'll notice, the friction loss for 500 gallons per minute, let me get my pen again. 500 gallons per minute is 1.66 feet per 100 feet of straight run of pipe. Okay, 500 gallons per minute. We're using the same values that we've had. Remember that we calculated the velocity, we calculated the velocity pressure, and now we are looking at the pressure drop for a section of 100-foot pipe. So I'm going to write that over here. I'm going to say it's 1.66 feet. That is the actual pressure drop. So if I put a pressure gauge over here for a moment, and actually I'm going to go to the next page here. Let's do this without messing it up. Yep. So if I put a pressure gauge over here for a moment, there's a pressure gauge there. Let's say the flow is from left to right. And then I put another pressure gauge here for a horizontal piece of pipe, no change in elevation. And it's pumping 500 gallons per minute or moving 500 gallons per minute. The pressure drop would be 1.66 feet. So in other words, if the pressure measured on the left side here, I'm just making up a number here. Let's say that pressure was 10 feet, then we would subtract out that 1.66, and that would be considered the loss for that 100-foot piece of pipe. So that's 10.00. And you can do the arithmetic. I'll do it on my calculator just so we have a number on the screen. So that's 10 minus 1.66, which is 8.34. 8.34. Whoops, that's not the best 8 in the world, is it, Brett?
Yeah, a little tough.
Little tough for Tuesday. So that means that this gauge here would read 8.34 feet, assuming again there's no change in elevation, and this gauge would read 10 feet because there'd be a pressure drop of 1.66 feet for that entire length. So when it comes to fittings, what we're interested in knowing is what is the equivalent length of straight pipe for a fitting. So let's go down here and using our same example, let's look at 6-inch for a moment. There's that 6-inch pipe. And if we had a standard elbow in that pipe, it would have the equivalent length or the equivalent pressure drop of 16 feet of straight pipe. So you can see that a standard elbow has a relatively high pressure drop as compared to, I'm just going to skip the medium radius, as compared to a long radius elbow. And then here's another one here. Here's a 45 degree. Now I'm going to go over here and look at what happens to a gate valve. So a gate valve, as the name implies, it has a gate that's inside here, and the gate rises up and is no longer in the water flow. So for all practical purposes, it's a minimal pressure drop, but it still has some pressure drop. And it has the equivalent of 3.5 feet of straight pipe. But look what happens over here if you use a globe valve. This has 160 feet, which means that we would take this 1.66 feet per 100 feet. I should have written that over here, per 100 feet. And I would multiply that by 160 divided by 100, which would be 1.6 times, if I can say equal over here, and then I kind of make a little arrow. That would be 1.6 times the pressure drop of 100 feet of pipe. So in other words, if my pressure drop was 1.66 feet per 100 feet, the pressure drop in this globe valve would be equal 1.66 times 1.6 comes out to 2.65. So you can see the pressure drop in a globe valve would be substantial compared to 100 feet of straight run of pipe. Now, the most of us would never use a globe valve in a conventional sort of HVAC system in terms of flow. You wouldn't put that globe valve in your piping system for the main flow characteristics of the system. But you might put a globe valve, for example, in a drain pipe or something like that. But typically you would use in smaller pipe a ball valve, and I would recommend a full port ball valve because the pressure drop is negligible. Or for larger systems, you might use a butterfly valve. And occasionally we do see gate valves that are used, depending on the pressure of the system. So hopefully you get an idea that you can account for pressure losses or friction losses through pipe fittings by using a table like this. And again, there are multiple tables on the internet. You can just type in friction loss for valves and fittings, and you'll get a whole range of tables. And again, that's how I got this one. Simple and straightforward as that. Any questions, Brett?
Yeah, great question here. Why is the pressure drop so much higher comparing globe and gate valves?
Well, a gate valve, I don't know if you're familiar with the gate valves. Let me try to make a sketch of a gate valve. Let's say we're looking at this end of the gate valve here. So you actually see inside the valve, so there's the kind of the top of the valve, and there's a stem. There's a disc inside here. And that disc actually rises up inside here. This is kind of a goofy drawing, so maybe I'll make it a little wider. And so that, it's almost like a guillotine. And when it rises up inside there, put a little handle at the top here. When that rises up, it's completely out of the water flow stream. But when it comes to a globe valve, if you ever look at the inside of a globe valve, this is kind of a goofy drawing here. But typically a globe valve has a seat in it like this. Usually there's a hole in the bottom of this thing like this. Let's see. And there's the inlet, and there's the outlet. And then there is a plunger that can actually close off depending on how that valve, there's the handle is up here. So this thing blocks this opening, but you can see the tortuous path when the valve is fully open. There's this tortuous path for the water to flow to a globe valve. So depending on the internal characteristics of the valve, it may have a substantial pressure drop, or it might have practically no pressure drop. Again, when it comes to smaller pipes, say 2-inch and smaller, most people will use ball valves, and a full port ball valve essentially has no restrictions in it, practically none. Everything has a small amount of restriction.
Would you suggest there's probably, I mean, you got to really think about what valves should take pressure loss and whatnot, but even for things getting hung up in them as well, like on a diaphragm valve or whatever, you know what I mean? You really got to think that through a little bit.
Yeah, and that's why, most engineering offices have a design criteria. We just listed a few for our pressure drop calculations, but they also have design criteria for the types of valves that should be used in the different types of piping systems, depending on what they're trying to do.
And then would you recommend general tables, or would it be more on a per manufacturer basis?
If you can get manufacturer's data, that's actually the best data. And if you don't have manufacturer's data, you can get generic data, such as this table is. When it comes to fittings like elbows, and T's and stuff like that, these generic tables are pretty good. But when it comes to the actual valves that are being used in the system, I would recommend that you go to the manufacturer's data. It's much more accurate than some of these generic tables.
And then someone mentioned that there are equivalent lengths for every type of fitting, maybe even a reducing T or stuff like that as well. So you just got to make sure you kind of take that into account if you're getting that close.
Yeah, that's a good point. I mean, I just copied one of the fitting tables that was available. They had like 20 or 30 pages worth of data, and I just copied one for training example purposes. Okay.
Excellent.
What is known as a valve CV, also known as the valve coefficient? And by definition, it's the flow in gallons per minute at a 1 psi pressure drop when the valve is 100% open. Okay, so let me try making a very simple sketch here. And let's say that I have a butterfly valve, and the butterfly, let's look at the direction of flow here for a moment. Let's say this is a section of pipe, and then we have a butterfly valve over here. Kind of make it a goofy looking thing like this. It's not the best drawing in the world. So if the valve is open, then we would see the disc in this direction here. Let's say the stem goes this way, and then there's a handle up here to rotate that valve. All right. And so if I look at that valve in terms of the direction of flow, let's say from left to right, and I look inside the valve, I'm basically just going to see the disc and the stem, very narrow disc like this, and then the stem coming up. So when the valve is 100% open, let's just assume that I'm just going to make up a number and say the CV for this valve happens to be, and let's say it's a 2-inch ball valve. I'm sorry, 2-inch butterfly valve. Make it simple. Actually, I'm just going to make it 4-inch because it's more common to find a butterfly valve at larger sizes. It's a 4-inch, and let's assume that the CV for a 4-inch, and I'm making this number up, by the way. You'd have to look it up and see what it actually is. But let's say the CV was 100. I'll just make up a number here. I don't know if this is right or wrong. What that means is that it will allow 100 gallons per minute, just like the definition says, 100 GPM, and the pressure drop across that valve is going to be equal to 1 PSI. 1 PSI. So that's the definition of a CV. And so we have, the nice feature about this sort of number is that we can compare different valves. Given the same pressure drop, we can see what the flow would be. So if I needed to have a fixed pressure drop, by the way, 1 psi is equivalent to 2.31 feet. And I think we've seen this value in the past in some of our discussions, 2.31 feet. So if I'm trying to compare, say, 2 or 3 different types of valves, and they all have the same pressure drop, but they have different flow rates in order to achieve that 1 psi pressure drop. So if I needed a valve that had a let's say that had a CV of 100, or let me put it a different way. If I wanted to limit the pressure drop to my valve at 1 psi, and I knew what I needed for a flow, then I would just simply pick a valve that had the same flow value that I wanted at that 1 psi. I hope I haven't made that too confusing.
Yeah, CVs are it's hard to explain. It's easy, but it's hard to explain, you know. But I thought you covered it pretty well.
Yeah, so the CV is actually the GPM. So whenever you see the value for CV, if you happen to see the value, let's assume, I'll just make up a number and say you're looking at a valve and had a CV of 20, that means it'll pass 20 gallons per minute with a 1 pound pressure drop. If it had a CV of 30, it would pass 30 gallons per minute at a 1 pound pressure drop. Good stuff.
Yep.
All right. So given this example, a valve with a CV of 25 will have a pressure drop of 1 psi at 25 gallons per minute. It's as simple and straightforward as that. And the units that we use is the CV units are is gallon per minute at 1 psi. If it happens to be a metric system, they use the term kV, and it would either be in cubic feet per hour or 1 bar, or be cubic feet per hour at 1 bar. And here are the conversions between the two. So if you had a valve manufacturer that provided you the value as a kV value, you would multiply the kV times 1.17 to get the CV value. And conversely, if you were given the CV value of a valve, you'd multiply it by 0.86 in order to get the kV value, depending on whether you're working in the metric system or you're working with US units. So let's just look at a couple of quick examples of a TACO zone sentry valve. And these are fairly small valves. So we'll just look at the 3/4 inch for a moment. And the 3/4 inch has a CV of 10.3. What does that mean? That means that that valve will allow 10.3 gallons per minute to pass through it when the valve is 100% open with a 1 pound pressure drop. And again, the kV value is simply the equivalent metric value that we just showed you the conversion for. And this shows us the equivalent length of feet in a straight run of pipe. So it has the same pressure drop for a 3/4 inch pipe of 8.4 feet. Good stuff.
Yep. Well, what is the difference? Okay. Oh no, KV and CV values. I think you covered that, so we're all set there.
Okay. All right. So now let's talk about how you actually calculate the pressure drop in the system manually. So here's a very, very simple piping system. It's a hot water heating system. It's primary flow. It has only 1 fan coil in it. It's got a boiler, and it's got a few components like an air separator, air and dirt separator. It's got the boiler, it's got the fan coil, it's got a control valve. So we want to figure out what the pressure drop is. We're going to use the point-to-point method. The point-to-point method, we're going to number each point. So as it exits the boiler, we're going to call, I think I'll change that pen color, Brett. Let me try a different color here. Might be a little easier to see. What if I put it in black? So that's point number 1. I'll put a little flag on it so you know it's point number 1. And the entrance to the pump is point number 2. And if you'll notice, we have the length of that pipe is 2.5 feet. I'm sorry, the diameter of the pipe is 2.5 inches and the length of the pipe is 2 feet. All right. And then we're going to look at the pressure drop of that section of pipe. And then after we take that section, we're going to take the next one. The discharge side of the pump is point number 3. Go all the way down here to the inlet to the fan coil. That's point number 4. So we're going to look at the pressure drop from point 1 to point 2, and then from point 3 to point 4, and so on. And I'll show you another chart, another diagram with all the points labeled on it. And I got ahead of myself a little bit. So one thing I wanted to point out is, why did we pick 2.5-inch pipe for the system? Well, if we'll notice, the flow in this system is 61.5 gallons. So let's go back to our pipe chart that we looked at a few minutes ago. Let's see if we can go over here. So we're repeating our design criteria. We want to have a maximum velocity of 8 feet per second or less, maximum pressure drop of 4 feet per second. I'm sorry, 4 feet per 100 feet. I'm getting ahead of myself. All right, so if we look over here, we'd say, okay, well, let's consider initially, let's say we want to use 2-inch pipe for our system. We know that our flow is 61.5 gallons per minute. That's close to 60. Should probably change that color back to red again. Let's try that, see how that works. It's a little bit more than 60, which means that our velocity is going to be a little bit more than 5.74 feet per second. Well, we said we wanted a maximum velocity of 8 feet per second, so it meets that criteria. But we also said we wanted to have a maximum pressure drop of 4 feet per 100 feet. Well, look at the pressure drop here. The pressure drop is 6.59 feet per 100 feet. So that would exceed our design criteria. So we go up to the next pipe size. So now we look at 2.5-inch, and we'll see that the velocity again is relatively low, 4.02 feet per second. And look at the pressure drop is only 2.72 feet per 100 feet, and it's below the 4 feet per 100 feet. So that means the 2.5-inch pipe would be the appropriate size. And so that's how I decided on the size of the pipe for my little simple diagram. Any questions, Brett?
I'm going to wait till the end to ask this question that's up here. So go ahead.
Okay. So we look at our diagram. We're going to number the diagram from point to point. And this is like I showed you before. Leaving the boiler is point number 1. Then we go to point 2. Then the discharge of the pump is 3. The inlet of the fan coil, and so on all the way around. We get all the way back to the inlet of the boiler, which is point number 10. So we're going to account for the pressure drop associated with each section of this pipe. So let's put together a little spreadsheet chart. And here we have, the first one is for pipe and fittings, So from point 1 to point 2, we said we had 2.5-inch Schedule 40 steel pipe, and its length was 2 feet. You get that right off the diagram. And again, I'm not going to read every single one, but just let's go to item number 2. That's from point 3 to point 4. Again, same size pipe, 2.5-inch Schedule 40 steel pipe, and that had a length of 20 feet. And so those different points, till we get all the way down to point 9 to point 10, we're just looking at the actual pressure, the length of pipe. Now, we've got 90-degree elbows, so we have to account for those. So I'm going to go back here to that diagram. Let's go back. And we're just simply going to count the number of elbows that we have for the entire system, starting at leaving point 1. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 over here. 11, 12, 13. We've got 13 elbows. 13 elbows. And what did I actually use in the table? If you'll notice, I used 20. So I typically, when I'm doing calculations like this, I take the actual length of pipe, but then I usually use some number of fittings. In this case, the 90-degree standard elbows. So I'm going to use a number that's greater than the number that's on the diagram because I want a little safety factor in there. You can use, depending on your office design criteria, most people will use a factor of 1.5 times. So if we had roughly 13 or 14 elbows, that would be, say, 13 times 6.5, which is 19.5. So I rounded it off to 20. And what's the equivalent length of a standard elbow for 2.5-inch Schedule 40 steel pipe? The equivalent length is 6.5 feet per elbow. Multiplying that by 20, that's 130 equivalent feet. And I add that to the length of pipe. So what's the length of pipe? Well, it's 20 plus 20 is 40, 42, 46, 48, 48. I do that right? No, I'm sorry, 246. Oh, I'm really going crazy today, Brett. So that's 46 plus 130, that's 176. So my total equivalent length of pipe, including the length of pipe and the equivalent length for the fittings, is 176. And the pressure drop we got from the previous table is 2.72 feet per 100 feet. And if I multiply that all out, it comes out to approximately 5 feet. So for my pipe and fittings, I have a pressure drop of 5 feet. Any questions about how I arrived at that value?
Nope.
Okay. We're going to skip over that table because we already looked at those. So now we're going to account for the equipment and the control valves. So here's a question for the audience. So I have one of the first devices from 0.4 to 0.5. I have a fan coil, and the pressure drop through that fan coil is 10 feet. There it is right there. This is a trick question, so I'm going to tell you right up front. How did I calculate the pressure drop in the fan coil? So this is a trick question. So if anybody's out there, Brett, can anybody tell us how I calculated that? I'm going to give it a few seconds.
Do, 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 do,
Yeah,
do,
this is like,
do. Jeopardy.
you sound just like the TV show, Brett.
Eric says manufacturer's data.
That's correct.
Cut
I did
sheet,
not
she
calculate
says.
the value. That's
Andy
true.
said the same thing. So we've got some, we got some answers here. Three different answers, but all the same.
Excellent. So the point is that you cannot calculate the pressure drop of somebody's piece of equipment. You have to go to the manufacturer's data, and you have to find, either by looking at their information online, or you may have to call up the manufacturer and say, I've selected this model fan coil. I can't find the pressure drop. And when it comes to fan coils, by the way, the most manufacturers have pretty detailed information regarding the pressure drop characteristics. So you have to go to the manufacturer, and that's the only place on the planet that you can get it. You cannot calculate it. You have to have them give it to you. The control valve. In this case, I found the control valve online that has a CV of 50. Remember what that means. That means that the control valve will allow a 1 pound pressure drop with a flow of 50 gallons per minute. Well, in our system, we just said that the flow was 61.5 gallons per minute. So in order to figure out what the pressure drop would be, well, it's 1 at 50 gallons per minute. So I would take 61.5. Let's do this over here. 61.5. Yeah. Divided by what the CV is of the valve. In this case, it's 50. And I take that value and I square it. And I multiply it by the pressure drop at 50 gallons per minute. So I'm using my calculator here, 61.5 divided by 50, that ratio comes out to 1.23. And if I square that value, it comes out to approximately 1.51. 1.51. I multiply that times my pressure drop. Remember, the CV is always, the pressure drop at the CV rating is always 1. So basically, I put a 1 in there. But that's in pounds per square inch, and I want to convert that into feet. So I multiply that value times 2.31. See if I do this right the first time, 2.31, and that is equivalent to, I know I'm kind of going vertically here, times 2.31, and magically comes out to approximately 3.5. 3.5. Hopefully, if you are following along in this calculation, it's 3.5 feet. And what did I use here? There it is. That's how I came up with that magic number of 3.5. But when I extended it over here, I rounded it off to 4. Again, let's go on to the next one, the air separator, same as the fan coil. The only place you can get that pressure drop data is from the manufacturer. In this case, it happens to be 5 feet. The boiler can only get that from the manufacturer's 11 feet. So if I add up all those values, it comes out to 30 feet. There's my value there. And from the previous page, it was 4.7. So our pressure drop for our system is 34.7. And that's the total pressure drop, including pipe, fittings, equipment, and control valves. Any questions about how I arrived at that number?
Oh,
This is exciting stuff. Okay, so here's my diagram. And we just said, let's just go back just to make sure I write this down so I don't goof up, Brett, and say the wrong number. We just calculated the pressure drop manually to be 34.7 feet, given this little system diagram, 34.7. And now if we go back here, that wasn't that good. Here's our diagram. Now, for those of you that are familiar with our HSS software or HS2 software, one of the benefits of using software is that it'll do the pressure drop calculation for you once you put in the right pipe lengths, pipe sizes, and the right components. So when I did it on the HS2 software, lo and behold, if I take the little green, this little green tag away, calculated pressure drop is 34.7 feet. Total pressure drop, 34.7 feet, and I'm multiplying that by a factor, safety factor, 15%. So my total pressure drop of my system is 40 feet after I add the safety factor, 15%. So therefore, I'm going to select a pump at 65 gallons per minute at 40 feet. Now, the pump itself is 61.5. I rounded it up to 65 gallons per minute. I made my selection at 40 feet. So let's just go here, and there it is. There's the pressure drop that the HS2 software has calculated at 34.7 feet. Now, the HS2 software has put in a fitting factor of 1.5 for the elbows, which is approximately what I did also. But it does not put in an overall safety factor for the system. That's something you have to add. And generally speaking, that's a function of your office design criteria. So whatever the criteria you have that you've established in your office, that's the value that you would use. Well, we've covered all of the material that I wanted to cover in this little discussion. I think that's the last slide. Is there another one after? Yep, that's it. So it's a little short today, but we did cover a lot of material. And hopefully, maybe we've generated some questions, Brett. Do we have anything out there that we can help folks with?
yeah, we have a couple questions. So I'm gonna read it as it is here. Why not use equivalent length instead of CV for the control valves?
Oh, that's a very good question. So you want to get the pressure drop, published pressure drop data from the manufacturer. And when it comes to control valves, generally speaking, most manufacturers represent the pressure drop in a control valve as a CV value. So they'll publish the CV value for the control valve. They generally do not publish the equivalent feet. Although in the table that I showed you that we at TACO use, I'm going to go back here to this table for a moment, all the way back here. We actually show you what the equivalent length in feet is. So this value we said we were looking at 3/4 inch. There's the CV 10.3. That's the flow in gallons per minute at a 1 pound pressure drop. And this particular valve has the equivalent length of 8.4 feet for 3/4 inch copper pipe. So you could use the feet value, the equivalent length value, but most manufacturers will just give you the CV of the valve, and most American manufacturers only give you a CV. They won't give you the metric equivalent.
And so question number 2, if you go back to your diagram,
Okay.
where the expansion tank connects, there's probably a little fitting there, T or whatever. Would there be some pressure loss for that too?
There would be, and it's kind of a judgment call. Remember, we added 15%. Let's go back here. We added 15% to the final calculation. So 15% safety factor, and that accounts for miscellaneous pressure drops that, which would include the connection of the expansion tank. It could include a whole series of things that we may not have data for. And that's why I tell people, I said, well, you have to establish an office criteria. And for simple HVAC systems, most people will use a safety factor of around 15 to 20%. If it's a more complex system, they might use a larger or higher value. But I think ASHRAE limits us to commercial systems to a maximum safety factor of 25%. If somebody in the audience knows that value, maybe they read it recently in ASHRAE, but I think it's 25%. But let me know. What else we got out there, Brett?
I've heard of some shortcuts where you add up the equivalent, you add up the length of pipe and multiply it times 50%.
Well,
Anyways.
you know, it all depends on the methodology. How accurate do you want your pressure drop calculations to be?
Right.
And you know, with software today, by the way, we've shown you the manual method by which the software, most software is based on. And as you can see, there's a correlation between the HS2 diagram and the pressure drop calculation that was done with the software versus the manual version, and the numbers were identical. And the important thing to keep in mind is that you know, we're showing you the sort of the foundation of how pressure drop calculations are done manually. But we do recommend that you use software. Software can account for a lot of different things that you might miss, as long as your diagram that you're putting together is accurate. In other words, in our very, very simple system here, for example, let me just go over here and highlight the fan coil. In our very, very simple system, we have a fan coil that has very, very simple piping. In reality, that fan coil might have a strainer, it might have a balancing valve, a couple of isolation valves, and the more components that you show on your diagram, the more accurate your pressure drop calculation is going to be. But again, for today's presentation, we wanted to show you how you can do this calculation manually and how it compares to a software calculation using exactly the same data.
So this is an interesting question, and I think it's important to cover this. What important considerations for pressure drop should we have when the fluid temperature is higher? For example, 212 degrees, 18 degrees, 200 degrees, 250, whatever.
Well, it's interesting because what happens when you increase, this is a weird thing. So what happens when you increase the water temperature, the specific gravity actually goes down. And so the pounds per hour that you're moving through the system actually changes. So for the same amount of flow and pressure drop, it takes less horsepower to move hotter water than it does colder water. That most of us know that. But I have a feeling the question came from the direction of well, how does the pressure drop calculation affect the net positive suction head required by the pump?
Could be.
So, so you know, the system that we've shown today is a very, very simple, basic system to demonstrate how to do manual calculation, how that compares with software. And it's assumed by the diagram that it's a closed loop pressurized system. And we know that because it has an expansion tank and there's nothing on the diagram that says it's open to the atmosphere. So when you increase the water temperature, you could potentially have a problem with cavitation if the pressure at the inlet of the pump, the absolute pressure, when you do the calculation for net positive suction head available, it's possible that the available pressure at very high temperatures would be lower than the required pressure by the pump, in which case for high temperature systems, especially when the pump is at the top of the system, you could potentially have a cavitation issue. And again, that's because the net positive suction head available is less than what's required by the pump. And generally you get into that problem in a closed loop pressurized system when you have high temperatures and the pump is at the top of the building.
So although you don't show any balance valves, what do you use for balance valves in calculations? Data, right, from the manufacturer, I guess.
Yeah, exactly. You would go to the manufacturer's data and you would see what they have for published data for balancing valves or any other type of valve that you would have, a strainer. I worked on a project not that long ago, it's about 3 or 4 weeks ago now, where the pressure drop when they did the manual calculation and the computerized calculation, indicated that the pressure drop, in our case, it would be from 0.1 to 0.2, was relatively low when they did the calculation. But when they did the measurements, they did the actual measurements, the pressure drop was much greater than what the calculation indicated. And so they had to go back to the manufacturer's data for all the components that were in the system. And it turned out that the pressure drop for the basket strainer was much greater in reality than what was published from the manufacturer. Now, beyond that, I didn't get into the depth of the reason why that happened. My job was to help the customer identify where the pressure drop was. And then once they figured that out, it was up to them to come up with a solution.
And someone wants to make sure we emphasize that, and you stated at the beginning, the fluid in this system is water. And if it's chilled water with glycol or hot water with glycol, you do need to look into the properties of that. It does change, or it could change the system.
Yes, so the pressure drop, this calculation today was based on water, but if you're using a different fluid, say the most common fluid out there is probably 30 to 40% propylene glycol. It's not the only one, but it's a very common one. And so you would have to use the characteristics associated with that fluid, both in terms of its specific gravity and relative to its viscosity or pressure drop in terms of equivalent length.
And way back at the beginning, someone asked the question, and this is the one I skipped over. What's the difference between KV and KVS? He sees that in some manufacturers' literature. I have it on my phone. If you don't know.
Well, yeah, if you could help me, Brett, what is, I'm not sure what you're referring to.
Here, when I Googled it, it says KV is the flow that generates a pressure drop of 1 bar at a given degree of openness. KVS is the flow that generates a pressure drop of 1 bar when the valve opening is maximum.
Oh, that's interesting. So they define it as KVS is the valve 100% open, and then the KV is the position at some intermediate position.
Yeah, it's a little crazy there, because I don't think every manufacturer shows both numbers, or at least
no, we don't. When it comes to our valves, we just show the KV value. I'm sorry, the CV value at 100% open.
Yeah. So,
well, that's a little interesting tidbit.
Yeah, I know. It's typical, Rich. We learn so much when we talk to experts that are on the call. It's
yeah, there's always something to be learned on both sides of the fence. So that's great information.
Yeah, and then someone's asking, is 30% glycol maximum? And the answer, well, I'll let you answer that one.
No, I mean, we've seen, especially, I guess, we worked with some folks up in Alaska. It's typical for them to use 50% glycol. They typically use a combination. Actually, I remember being up there a couple of years ago, and I asked that same question. And they for some parts of their system, they use ethylene glycol, and other parts they use propylene glycol. But generally speaking, they said that their concentrations are about 50%.
Yeah. And then the last but not least, and I'm not sure how you're going to, anyways, would we change pressure within the boiler if the pump is installed on the return? Not sure what.
Well, that has really to do with what's the minimum and maximum pressure and what the safety relief valve is going to be. So yeah, it all depends on how you want to place the pump. Again, this diagram is strictly for instructional purposes. It's not intended to be, an actual design. It's just for calculation purposes.
Yeah, don't take a picture of it and send it to a contractor, please.
Yeah, don't do that.
Please. And say you got it from Rich and Brett. That would even be worse.
Yeah, that wouldn't be a good day.
No, that's not a good day.
Don't do this at home. Is that how the expression goes?
Yeah, there you go. Well, I think we've wrapped up the questions, my friend.
Well, that's great. So I'm going to turn it over to Brett in a couple of seconds here, but I do want to say, have the opportunity to say thank you very much, and hopefully the audience out there is going to participate in some type of holiday get together. So happy holidays for everyone in the audience, and I hope you have a great time with family and friends this time of year. And I'm going to turn it over to Brett. So I'm going to sign off, and thanks again. Really appreciate it.
Thanks, Rich. Great job. And I don't think Rich and or I can emphasize enough. Use software to do what Rich just did. Learn it, understand it, but use software.
Yeah, I don't recommend that. I mean, when I first started in the industry, there was no software, and you know, but I mean, you have to understand the principles of these calculations. But yeah, software is very sophisticated today, and as long as you're using it properly, you'll find you'll get great results.
And we've talked about this on other presentations. This software also keeps track of the volume of the water or the fluid in the system as well to help you size expansion tanks. If you need more information on that, get in touch with us, and we can surely give you more information on it. So that's an important calculation that we talk about as well. So, Rich,
Happy
great job.
holidays.
Happy holidays, everybody. Thank you for attending. And, I recognize quite a few names on here, and thanks for putting up with us the past year or two or longer. And I'm sure we'll see you down the road. But signing off from New England, Cranston, Rhode Island, and Massachusetts, where Rich is. Duxbury, is it Duxbury, Matt?
It's
Rich?
Duxbury.
On the south shore of, he lives between Boston and Cape Cod, for anybody that
Cape
wants
Cod.
to.
Is that how you say that? Cape Cod.
Across the street from some
Cranberry bogs.
cranberry
Yeah, I'm
bogs.
looking out my window right now, and I can actually see the cranberry bogs. They've already harvested them this year. They usually harvest them in October. But yeah, I live in the middle of cranberry country.
We've covered enough. Thanks, everybody. Take care.
Take care.
Bye. Bye.